All right, my friends, today we are going to jump into our second gas law, and this is going to be all about Charles' law. Now, last time we talked about Boyle's law, and we talked about the inversely proportional relationship between both pressure and volume. Today's is going to focus on the relationship between volume and temperature. And again, a scientist named Charles did find out that this was the relationship, which is why this law is named the way it is. Okay, so here's my little example. Again, not an artist, sorry guys, but I want you to think about if I were to take a balloon and let's say I left it out in the sun. So you would say the temperature is high. So when the temperature is high, the gas particles tend to speed up and start to expand that balloon. So the volume is probably also going to be high. So when the temperature goes up, the volume decreases. And this is also an experiment you guys can feel free to do at home. All right, so high temperature is equivalent to a high volume. But what if I lower the temperature? Let's say I stuck that balloon in the fridge, and these are ice cubes. Cute little ice cubes. I stuck that balloon into the fridge. The particles are going to start to slow down. And let's say, sorry guys, don't look, that this means the temperature is low, because if I put that in the fridge, if I put that in the freezer, we know that the temperature is lower in those areas. The volume is going to start to decrease because the particles are going to start to come closer and closer together as they slow down. So this relationship is a little bit different, or a lot different, than the last relationship we talked about, in that when one goes up, the other does. And when one goes down, so does the other. So we say that this is a directly proportional relationship. And since we're talking about the relationship between volume and temperature, the definition of Charles' law is going to be that the volume of an ideal gas is directly proportional to its temperature. So just like in this model, what that means is when one goes up, so does the other. When one goes down, the other follows. And again, this is the relationship between volume, which we represent with a V, and temperature, which we represent with just a T. Since this relationship is inversely proportional, we say that the equation, or inversely, oh my goodness, I'm sorry guys, directly proportional, we say that the equation between volume 1 over temperature 1 is equivalent to volume 2 over temperature 2. When you rearrange it, you will calculate this definition in your relationship. So again, this is going to be before the change. And over here is going to be after the change. Now let's talk about units for this. We talked about the units for volume last time. V is going to be in liters, which is just L, but temperature. Now I know we're used to measuring temperature in Fahrenheit and Celsius. We're going to use for T kelvins. And that is just a K. It's not degrees K, it's just K. Now, a lot of the times you'll be given Celsius, so you actually have to calculate kelvins. Your degrees in Kelvin are going to be equivalent to, or I'm sorry, I said degrees in Kelvin. It's just Kelvin. There's no degrees. Sorry, guys. Kelvin is equivalent to degrees Celsius plus 273. So if you take your degrees Celsius and you add it to 273, you will get your temperature in kelvins. Make sure you are always solving for kelvins. You will likely be given Celsius. You need to convert that before you solve. All right, so Charles' law, we got a direct relationship between volume and temperature. This is the equation we use to solve. Let's jump into some practice problems. All right, so if we look at example 1, it says that a 2.5 liter volume of hydrogen measured at negative 100 degrees Celsius is warmed up to 100 degrees Celsius. Calculate the volume, so I'm looking for V2 of the gas at a higher temperature, assuming no change in pressure. And again, the pressure is staying constant, so we can just focus on that relationship between volume and temperature. I'm going to go back and label everything in my equation. So I know that this was my initial volume. This is my V1 of hydrogen was measured at this first temperature. There's my T1, and I know it warmed up to 100 from this negative 100 degrees. So this must be my T2. So now I'm going to write out the relationship as my first step. So V1 over T1 equals V2 over T2. I'm interested in finding V2. And if I think conceptually about Charles' law, I know that my temperature increased. So a good way to check yourself is remembering that relationship. My temperature increased, so my volume should be a larger number than the initial volume. So now that I have my equation right now, I'm going to go ahead and plug in my numbers with the units. And remember, we're calculating with significant figures. My first volume is 2.50 liters. There's 3 sig figs there. Over, and then, I have to do another step. I have to convert this to kelvins. So kelvins is going to be the degrees Celsius. So I have 100, negative 100 degrees Celsius, plus 273. Let me just calculate that real quick. If I plug that in, negative 100 plus 273 gives me 173 kelvins. Use this number. So I have 173 kelvins, and that's going to equal my unknown, which is V2, over T2. And again, I have to convert this 100 degrees into Kelvin. So kelvins is going to be equal to that 100 degrees Celsius plus 273. And I'm just going to do mental math here. It's going to be 373 kelvins. I'm going to plug that in here. Now, looking at this, if I really, really want to get my unknown by itself, I'm going to multiply both sides of my equation by 373. Remember to bring the units. Sorry, guys. 373. And I'm going to just rewrite it visually so that we can start canceling out units and assuring that we end up with the desired unit for our unknown. So now when I multiplied everything, these guys cancel. I have 373 Kelvin times 2.50 liters over my 173 degrees Kelvin. And when I look at this, I see that my temperatures were one significant figure. When you're converting to Kelvin, you do need the 3 numbers. So I'm just going to report this to 3 significant figures. So I'm going to plug everything in. Oh, whoops, sorry guys. 373 times 2.5 gives me 932.5. And I'm going to divide that whole thing by 173. And I'm reporting to 3 sig figs because I converted these units and I kind of need to keep that 73 there just to kind of keep everything clear. So I should have 5.39 liters. So I started with 2.5 liters. 5.39 is definitely a larger volume. So that's a good way to check and make sure that you've plugged everything in correctly. Because I know my temperature went up, which means my volume too went up. All right, example 2, and then we're going to jump into practice. I have 5.00 liters of gas collected at negative 173 degrees Celsius and then allowed to expand to 20 liters. What is the new temperature? So I'm looking for temperature 2 in order to maintain the same pressure. So again, the pressure is going to be constant, so it needs to kind of fit into that equation. Going back, this has to be my V1. This is my T1. Here's my V2, and this time I'm looking for my second temperature. I'm going to write out my equation for Charles' law because it's going to explain the relationship between both volume and temperature. And then I'm going to plug in my numbers. My first volume is 5.00 liters, which is 3 sig figs, over my temperature 1. Ooh, I need to convert that. So Kelvin is going to be negative 173 plus 273. And this is in degrees Celsius. That gives me negative 173 plus 273. My temperature in Kelvin, which is just 100 Kelvin. So over 100 Kelvin is going to equal my 20 liters over my T2. Now, this is a little tricky because I know as manipulating equations might be not our strongest point. What I would recommend is just bringing T2 over here so that it can then be on the top. So there's going to be another step here. I'm going to multiply everything on each side by T2, just so you guys can visually see what I'm doing. So now I have T2 times 5.00 liters over 100 Kelvin equals 20 liters. Now I'm interested in getting this by itself, meaning I need to multiply by the bottom number underneath the fraction bar and then divide by the top number. So step 4 is going to be over here. I'm going to multiply by this 100 so that I have T2 times 5.00 liters. Multiplying this side by 100 gets rid of the 100. Multiplying this side, I'll end up with 20 liters. And sorry, guys, this is going to be multiplied by that 100 Kelvin. And then I'm going to go ahead and divide by my 5.00 liters so I can cancel it. And I will rewrite this for you so you can see how I'm solving. T2 is going to equal 20.0 liters times that 100 Kelvin over 5.00 liters. And that is what I'm going to plug in for temperature 2. Now I see that the volume increased, which means my T2 when I solve should be larger than my initial temperature. So let's look at that. 20 times 100 divided by 5. And my temperature in Kelvin is 400 Kelvin. And again, I have to report to 3 significant figures because all my values in here have 3. So I'm just going to put a dot here so that it makes those zeros significant. Checking my work with the concept, my volume went up, my temperature also went up. So I probably did this work correct. And again, the only reason I didn't really use sig figs here was so you guys could get a clear visual of how I converted to kelvins. Please make sure you are paying attention to significant figures in your practice problems. All right, reach out with comments, emails, or remind. I'll be available most days until 3. Thanks, guys. Bye.